Hello, my name is Nathaniel. So you haven't seen me in quite a long time. So anyway, we're now going to do question 5 on step 2, 2020. Now this question relies on a did simple thing, well, mathematical procedure called congruency modulo 9. Sounds scary, right? Not that scary when you just realize it's just dividing by 9 and taking the remainder. Because the remainder is what we're interested in. Let's say you have a number, say 946. You want to know whether it's divisible by 9. So you add up all the digits. 9 plus 4 plus 6 is equal to 19. And we find that it is not divisible by 9. So this d function is basically called the sum of the digits and base 10, but you continue iterating d until you arrive at a fixed point, which is usually a single digit number. Then what you get is called the digital root, which is again the number modulo 9, which is take the remainder after you divide by 9. Right, so the second statement is a reminder of what base 10 notation really is. So it says that you have 10, but you can, for some reason, you can change the 10 to any kind of number you wish. Just don't change it to 1 or 0 for that matter, because they won't generate valid number systems, which is called positional notation. So you can create positional notation systems for all integers, yes, negative integers too, rational numbers, irrational numbers like the square root of 2, and imaginary numbers, of which there is base 2, I also call quarter imaginary. Now, prove that x minus dx is non-negative and divisible by 9. To do this, we need to consider the powers of 10. 10, 100, 1000, etc. Now, if you take the remainders modulo 9, you get 1, 1, and 1. And if you think about it, they actually had 1 all over the place, because you have a string of n 9s, where n is some integer, then it will be automatically be divisible by 9. So that means dx is equal to x modulo 9. And since d of x is always smaller than x, because you just eschew all the powers of 10, and then it will automatically become smaller, yes? So this means x, and so let's write this down. X is congruent, is written like this, is congruent to d of x mod 9. Usually we put the mod 9 in brackets. Now, prove that x minus 44 d of x is a multiple of 9 if only if x is a multiple of 9. This one's a bit harder, because now we have to say, suppose x is equal to 44 d of x. Actually, it's not equals anymore, it's congruent. So, again, we are assuming modulo 9, so, and we'll probably not write it. So, since 44 is negative 1 mod 9 or 8 mod 9, x equals the 8 of d of x. And guess what? The only numbers when this actually works is when x is congruent to 0 mod 9. That's right. So that means x minus 44 d of x is multiple of 9, and only if x is a multiple of 9. So that means x has to be a multiple of 396. Why? Because 44 times 9 is 396. Now, moving on, x equals to 44 d of x. Show that if x has not n digits, then x must be less than 396 of n, since d of x is always less than or equals to 9n. And then x must be greater than or equal to 10 to the power n minus 1, as an n digit number should have n digits, right? So that means x should be greater than 10 to the power n minus 1, and hence that n is less than or equal to 4. So 396 is obviously greater than, so when n is 1, you have 1. Then the next number of 396, 792 is greater than 10. Then 1188 is greater than 100, and 1584 is less than 1000. So far so good. However, and consider the next model, 1980 is less than 10,000. So this means n equals 1, 2, 3, and 4. So find a value of x for which x equals to 44 of d of x. So n has to be less than 4, because then you need to have it more than 4 digits. So the answer is 792. Checking all the solutions we use, that only 792 works. Why? Because 7 plus 9 plus 2 is 18, and 792 divided by 18 is, you guessed it, 44. Now, obviously, you can generalize this question to other bases and other types of numbers, like other numbers and other, scalar multiples. But obviously, we are only going to use 44 here, and then the next part we are now going to use 107. Now you're thinking, nested these in these, how is this even possible? Well, you can just write, so let us say x minus 107 ddx is equal to 0. I'm omitting the brackets here because it's quicker to write. So 107 x minus 107 dx plus 107 dx minus 107 ddx minus 106x equals to 0. Now, as you can see here, these look like derivatives, but actually they are not. They should have been using q, which is what they have put in the answer sheet all along, because q doesn't look like a derivative. Now, please, calculus students, don't confuse the derivatives. They are only using the d of x, which is the sum of all the digits in base 10. So, 107x minus dx plus 107 dx minus ddx minus 106x is equal to 0. Of course, this is divisible by 9, and this is also divisible by 9 because we can substitute dx for y and get y minus dy. Yeah, that's right. So x has to be divisible by 107 times 9, and if you do the calculation, it equals to 963. So x must be less than 963 and less than or equal to 963 and x is greater than or equal to 10 to the power n minus 1. And then you do the same procedure as mentioned before, you will find that n is less than or equal to 4. And you test out all 4 solutions, only n equals to 1, 963 works. Let's test out this solution by double checking. So 9 plus 6 plus 3 equals to 18. 1 plus 8 equals to 9. And we find that 9 times 107 is 963. Now, of course, this is only for base 10. Yeah? And you can generalize this trick. This is not even a trick anymore to other bases, of course. Like for base 16, you will have an analogous thing. Formula x minus dx is non-negative and divisible by 15. Yeah, that's right. And you can do congruency modulo whatever you want as long as it is the base minus 1. Just make sure that this base is the integer base or this function will completely flop and be destroyed. And no, not necessarily being destroyed. It's more like it's out of the domain. Well, anyways, see you in another step video and happy 2024 to you. Bye!